Hello, discrete math fans. Now we're going to talk about NAND and NOR gates. Now when you're a digital logic circuit designer, it's very important that you create the simplest possible circuit. The fewer the gates that get used, the less power that's used. Think about your cell phone. What is the one thing that's important on cell phones? The one thing that everybody complains about? Power usage. The fewer the gates that get used, the less power that's used, the less power that your cell phone will consume. The two types of gates that we haven't mentioned before are useful for simplifying gates. They're the NAND gates and the NOR gates. So a NAND gate is a single gate. It acts like an AND gate followed by a NOT gate. A NOR gate is a single gate that acts like an OR gate followed by a NOT gate. Now there are special symbols for NAND and NOR, just like we have for AND, OR, and NOT. So a logical symbol for NAND is this vertical bar. That's called the Sheffer stroke. Now you may be insistent upon using a vertical bar for OR. So in that case, I would recommend that you use a double vertical bar for that symbol and reserve this single vertical bar for the Sheffer stroke for NAND. Another symbol that you could use is this vertical arrow. That's a symbol for NAND. The symbol for NOR is this down arrow. That's called the Pierce arrow. And so we can say then that P NAND Q is logically equivalent to NOT, and then in parentheses, P and Q. Whereas P NOR Q is NOT, and then P or Q. Here's a table that summarizes everything with NAND and NOR gates. You can see that NAND is just taking two inputs, computing the AND of those two inputs, and then finishing by computing an OR. You see the symbol representation for the NAND when you write a gate looks just like the AND symbol, but then you put the little circle at the end that indicates that you're doing a NOT at the end. Same thing with the NOR. Okay, that's all for now.